Okay, so now we'll look at Lamport's algorithm for distributed mutual exclusion. So we'll go through an example to understand the working of the algorithm. Here we have three processes, and P1 and P3 want to access a critical section. P3 generates the request first, and remember the assumption of the algorithms here. We'll use the physical clocks at the processes, and they're loosely synchronized, so we will be able to distinguish the timestamps of the request messages. And even if there's a tie, if two requests have the same timestamp, we'll be able to distinguish based on the process IDs. So the process with the lower ID has the lowest timestamp in that case. So in this case, P3 generates the request first, and the way Lamport's algorithm works is the request message to access the critical section is broadcast to all the processes. So in this case, P3 broadcasts the request message to P1 and P2, and also queues that request along with the timestamp in its queue. So all the processes receiving that request message will also queue that request in the timestamp. Now, before P1 gets that request, it also wants to access critical section, so it generates a request message and broadcasts to the other processes. And so since it did not yet get P3's request to start with, it just puts its own request in its queue. But once P3's request comes in, it sees that P3's request was generated with an earlier timestamp, so it puts P3's request ahead of its own request in the queue. And likewise, when process P2 gets both the requests, it puts them in the increasing order of timestamps. So P3's request is ahead of the other process request in the queue, and P3 gets the request message of P1. So of course, since P3's request is having a lower timestamp than P1's request, P3 puts its own request ahead of P1's request in its queue. So as you can see, P3's request is in the front of the queue at all the processes. So now each process sends a reply back to the sender of the request message. So P3 sends a reply to P1. Similarly, P2 sends a reply to P1. And likewise, P1 sends a reply to P3, and P2 sends a reply to P3. So the two processes P1 and P3 that sent out the request messages would have got the reply messages too. Okay, so P1, P3 that sent the request would have got the reply. Alright, so now if you look at this, the process that has its request in the front of the queue, and the process that has received the reply for all its from all the processes is the only process that can access the critical section. So again, the requirement is to access the critical section, a process should have received the reply message from all the processes, all the other processes, and its own request should be in the front of the queue. So P3's own request is in the front of the queue, and it has received reply from the other two processes. Whereas P1's request is not in the front of the queue, some other process's request is in the front of the queue in P1. So even though it has received the reply messages from the other two processes, P1 cannot enter the critical section now. So only that process whose request is in the front of the queue can enter the critical section. So only P3 can enter the critical section. So it spends some time executing the critical section, and once it is done, it sends a release message to all the processes. So basically telling them to remove its request from the queue. So of course P3 also removes its own request from the queue, and P1 and P2 also remove P3's request from the queue. So now P1 can check whether its own request is in the front of the queue, and the answer is yes, and P1 has also received reply messages from the other two processes. So P1 can now enter the critical section, and then once it is done, it can send a release message to the other processes, and those processes can remove P1's request from the queue. So at the end, no process has any leftover request message in the queue because only these two requests were generated. So if you look at the message complexity, to access a critical section and to come out of it, a process has to send request messages to the other processes. So if you have n processes, each process has to send n minus 1 request message, one to each of the other processes, and then it has to collect n minus 1 reply messages, one from each of the other processes, as well as send out the release message to the other processes. So you have n minus 1 request, n minus 1 reply, and n minus 1 release messages. So it is 3 times n minus 1, which is basically theta of n. Now, in terms of synchronization delay, the release messages are sent to each of the other processes. So it takes one propagation delay for release message to go. It's a broadcast message broadcast to the other processes. So it is one propagation delay. And the system throughput is 1 over the synchronization delay plus execution time for the CS, so it is 1 over T plus E. Now, if you notice the working of this Lamport's algorithm, you could realize that the process P3, whose request is in the front of the queue, right? So after it got the request message from P1, P3 knows whose request is in the front of the queue. So P3 could kind of defer its reply. Instead of P3 need not send a reply to P1 because P3 knows that P1 will not be able to execute the critical section even if it sends a reply, because P3 knows its own request is in the front of the queue. So it knows that even in P1's queue, P3's request will be in the front of the queue ahead of P1's request. So there's nothing that P3 or P1 is going to achieve because of the reply message that P3 sending to P1. So P3 can defer its own request reply message. P3 can defer its reply message to P1 and just enter the critical section. But P1 has to send its reply message to P3 because P3's request timestamp is lower than P1's own request, and P3's request is in the front of the queue. So P1 has to send its reply to P3 as well as P2 has to send its reply to P3. So when P3 gets the reply messages from the other processes as well as its own request is in the front of the queue, P3 can enter the critical section. And once it is done with the critical section, it can send out the release message to P1. So it's a kind of, you don't need to send the reply if that particular process request is not in the front of the queue and yours own request is in the front of the queue. So you could defer the reply until you are done with the CS execution, and then you can send the release message to P1. So by this you are avoiding this reply message that you are sending to the particular process. So if you do this to the processes that have sent you the request and their request is behind your own request in the queue, then you can avoid all those reply messages and send out just the release messages. So the time complexity, in terms of the message complexity, you could reduce the number of messages. Basically, you can suppress the reply messages to the other competing processes and send out just release messages to them. So the number of messages can be reduced, and this would be now from anywhere from 2 to n minus 1 to 3 to n minus 1. So previously it was 3 times n minus 1. So now it could be from anywhere from 2 times n minus 1 to 3 times n minus 1. Now in terms of the correctness of the Lamport's algorithm with respect to 3 properties, safety, now you know that all the request messages are having a timestamp and they could be totally ordered. So you could say one process's timestamp is lower or larger than another process's timestamp, and as I said, even if there's a tie, you can break the tie based on the process IDs. So which means only one process's request message is going to be ahead in the front of the queue. So if you have all those request messages, like in this case P1 and P3's request messages, we know that when P3 is entering the critical section, only P3's request is in the front of the queue at all the processes. So basically the processes can order the timestamp request messages in the increasing order of the timestamps. And so even if a process has received the reply messages from the other processes, its own request is not going to be in the front of the queue if some other process has a lower timestamp than its own request. And similarly with the optimization, a process like P3 is going to defer its reply and send a release only after it is done with the CS execution. So a process like P1 should have received either a reply or release from all the other processes, and its own request has to be in the front of the queue. So there is no way more than one process is going to execute the CS at any time. So this way you can say the algorithm is providing you the safety property. In terms of blindness, what it means is a process that has made a CS execution request should be eventually be able to access a critical section. And again, the processes request are ordered in the increasing order of timestamps. So if a process has made a CS execution request and another process makes a request after this, and again, since the communication channels are FIFO and reliable, a request message sent by a process will definitely reach the other processes, and again the reply messages are going to reach back these processes. So which means the request made by a process is reaching every other process, and it gets enqueued. And since the requests are ordered in the increasing order of timestamps, definitely a particular process's request will get a chance to move ahead in the queue with each request being completed, and at some point of time it will be in the front of the queue, and the process would have received all the reply messages and it can enter the critical section. So it provides you the liveness property as well as fairness, because again the process request order the increasing order of timestamps. So a process that has made a request earlier would get a chance to definitely get a chance to execute the critical section compared to a process that made a request later. So this way we provide fairness also.